Welcome back. We will continue module 2, strings and exact matching. Today's topic is suffix arrays. We concluded the last lecture with the Z algorithm. So, we had started this problem of exact pattern matching, where we defined the problem as given a string P, which we were referring as a pattern, and a longer string T, which we were referring to as the text. The exact matching problem is to find all occurrences of pattern P in text T. In the last lecture, we attempted to solve this problem using Z algorithm, so the runtime complexity of the algorithm was linear in the pattern and the text size. So, for Z algorithm, we solved the exact pattern matching problem in order P plus order T, that is linear in the pattern size plus the text size. The key building block of the Z algorithm was this concept known as Z array. Once we defined the Z array, then solving the exact pattern matching problem was straightforward. So, we will continue with this exact pattern matching problem. Today's topic is to solve this problem using text pre-processing. We will look at popular index such as k-mer index, suffix arrays, and then we will subsequently start our discussion on the algorithms that we can use to efficiently build the suffix arrays. So, let us start the topic of index assisted algorithms, and within that we are majorly going to focus on suffix arrays. So, in the last lecture we were looking at an example or a situation where the text is given at runtime. So, for example, if the text is given to at runtime, then we do not have the opportunity to do any homework or any pre-processing on the text. Whereas, if the text is known in advance, so if the text is known in advance, then what we can do is we can do some pre-processing on the text. We can try to build some indexes so that we can do the pattern matching more efficiently. The goal will be that so remember that in the Z algorithm and many other algorithms like KMP and Boyer-Moore, the exact pattern matching problem can be solved in linear time, that is order P plus T. When the text is known in advance, our goal will be to achieve a time complexity that is sublinear in terms of the text size, because normally the text size is going to be very big, and if we are envisioning that we are going to have a common text, but we are going to have too many pattern queries on that text, then it makes sense to build an index so that the pattern matching can be done more efficiently. So, the aim would be to achieve time complexity that is sublinear in terms of the text size. Okay. So, let us start this discussion, and first let us see why do we want to index. One key argument here is that the bioinformatics sequences are very large. So, for example, if you look at the human genome reference, it is 3.2 gigabases long. So, it has 3.2 billion nucleotide characters. In the pine genome, for example, we have that is an even longer genome. So, there we have 12 billion nucleotide characters. If we look at raw sequencing data sets such as coming from metagenomics, then there we even have bigger data sets ranging from 100 to 1000 gigabases. If we look at the complete SRA public database, which has all the publicly available sequencing data, it goes to 50 petabases in size. And given that if we want to enable any pattern matching on these large data corpus, then we need efficient indexing strategies so that we can do efficient pattern matching on these large data repositories. Now, one thing that we should say here is that the structured text, for example, natural languages like English text, websites, English documents, textbooks, there you can say that the text is relatively easier to index, because there the text is structured in terms of English words and those words have certain grammar. So, there the indexing strategies are relatively different and we can tokenize the document in terms of words. Whereas in genomic sequences the text is unstructured, that means that we will see just contiguous stretches of A, C, G and T characters, and these strings can be going from like starting from 1 million to 250 even 500 million nucleotide characters long. So, it will be all just sequence of A, T, C's and G's, and there is no visible structure on in terms of the words like we see in the English text. Now, given the size of these data sets and these databases continue to grow, there is always a need to design efficient algorithms to enable pattern matching on these data repositories. So, given the growing databases, this indexing or efficient indexing of biological sequence databases remains an active research area. So, let us start with the simplest index that we can think of, which is a k-mer index. Now, this k-mer index is very similar to the inverted file data structure that is typically used by web search engines such as Google. What a inverted file means is that there we will have the vocabulary in terms of the words that we want to index. For example, in this example I am indexing nouns and adjectives, and I am keeping track of the positions in the text at which these words occur. So, for example, if my document is this, where the text says that house has a garden, the garden has many flowers and the flowers are beautiful. So, if I want to build an inverted file index for this document, then I would build a lexicographically sorted vocabulary where all the words in the vocabulary will be lexicographically sorted. So, the word beautiful will occur first, then flowers, then garden and then house, and for each word I am going to keep track of the position at which that word occurs. So, for example, the beautiful word occurs at position 70, the flowers word occur at twice, that is at position 45 and starting at position 58 and so on. So, this is the classical index that is used for indexing text documents and web documents. So, extending the same idea, the idea of k-mer index is to basically index all k-mers, and by k-mers I mean the k size substrings in my biological text T. So, in this case, if suppose k is 5, then I would consider all substrings of length 5. So, in this case all substrings of length 5 will be considered as words in this document, and I am going to build a lexicographically sorted table of all distinct k sized substrings. For each substring I am going to keep a track of the positions at which those substrings or k-mers occur. So, for example, the k-mer CGTGC occurs at position 0 and position 4. Now, we can ask, given this such a k-mer index where your distinct k-mers are lexicographically sorted, and for each k-mer in this k-mer table, for each k-mer we have kept track of the locations at which those k-mers are occurring. How can we query a pattern using such an index? So, suppose I give you a pattern T, G, C, T. So, suppose this is my pattern. How should I go about searching for this pattern in my text? And suppose we have already built such a k-mer index to accelerate my pattern searching. Well, a straightforward way to do this pattern matching now, because all these distinct k-mers are lexicographically sorted, all I need to do is look for the first character and do a binary search on the first column. In the binary search I would look for the character T and find the range, the starting and the ending range at which the character occurs. So, in this case the start and the end range would be this. Then I would move to the next character of the pattern, which is G. I would continue by binary search within this particular range, and it turns out that all the characters correspond to G. The next I will move to C. Again I will do a binary search in general scenario, and similarly for the fourth character I will do a binary search in this region and narrow down my search to the last row. This particular row will immediately tell me that the pattern that I am looking for occurs at position 6 in the text T. So if we look at the search time now, so if the pattern is of length P, so let me say that pattern is of length P, then I am doing P iterations of binary search. So I am doing P iterations of binary search, and the range of each binary search can be as big as T. So remember that the binary search on a column of size T will take log T time. So this gives me a complexity of order P log T, but this is assuming that the pattern length is less than equal to K. If the pattern exceeds the length of K, so if my pattern length exceeds K, then what do I do? Note that if the pattern length exceeds K, I can do K iterations of binary search, but I cannot search for K plus 1, K plus 2th character in this using this index. So this is one of the drawbacks of the k-mer index, that the patterns that it allows you to search must be less than equal to K. So that with that deficiency, the k-mer index can be used to search for patterns of length K or patterns of length less than K. Okay. So that was the simplest index that we could think of, is the k-mer index, in which we keep track of all the distinct k-mers and their location of occurrences in the text. Let us move to a more sophisticated index, which will in particular address the deficiency or address the drawback that the k-mer index had, that is, it was not able to search for patterns of length greater than K. So we need an index that would allow searching for patterns of arbitrary length. So it should not have any constraint that pattern should have any particular length. We want to design an index where there is no constraint on the length of the pattern. So suffix array is one of the data structure that resolves that limitation. This data structure was proposed in 1993 by Manber and Myers, and to this day the suffix array data structure continues to be used in many algorithms, especially genome alignment algorithms. So let us understand this suffix array data structure in more details. Again, the definition of suffix array is very straightforward. By suffix array, all we mean is that it is a lexicographically ordered array of all the suffixes of text T. So for example, if my text T is Mississippi, I am going to also make an assumption that my text ends with a dollar character. One can ask, why am I making that assumption? Well, the reason is that if you consider two suffixes, let us say pi and ppi, so pi and ppi, their lexicographical ordering is ambiguous, because it is difficult to say whether pi is less than ppi or ppi is less than pi. So to remove that ambiguity, what we do is we append a dollar character in the end of the text. We assume that this special character is not in our original alphabet, so this is a special symbol. We will assume that this symbol is smaller than all the other characters of the alphabet. So in this case, dollar is assumed to be less than A, which is less than B, and so on. So with that assumption that the text ends with a special dollar symbol, let us see how the suffix array will look like. So now given the text T, which is Mississippi dollar, we are going to see all the suffixes of this text T. So the suffixes of this text T are dollar, I dollar, PI dollar, PPI dollar, and so on. So all the suffixes are being considered in the right hand side figure. The suffix array will be defined by the lexicographically ordered array of the suffixes. So we need to sort these suffixes, and the ordering of these suffixes will give us the suffix array. So again, continuing the Mississippi example, considering all the suffixes here, what we do is we sort these suffixes lexicographically. So if we sort the suffixes lexicographically, then automatically the suffix dollar will appear first, because it is the lexicographically smallest suffix among all the suffixes. The next smaller suffix is I dollar. The next lexicographically smaller suffix in this text is IPPI dollar, and so on. And finally, the last suffix in this ordering will be SSI CCPP, because S is a lexicographically bigger character. Now once we do the sorting of all the suffixes, the suffix array will tell the sorted order of these suffixes. So in my suffix array, I am going to only store the indexes of these suffixes. So the first entry of the suffix array will be 11, telling that the suffix starting from position 11 should occur first in the lexicographical order. Similarly, suffix starting at position 10, which is I dollar, should occur next in the lexicographical order, and so on. So when I am storing the suffix array, all I will be doing is I will be storing this list of integers, that is the list of suffix indices. I am not going to store the actual suffixes, because I can always access the suffix from this index. So for example, if I need to know the suffix corresponding to this index, I can always refer back to the text and I can get back my suffix. So in this particular case, because my indexing was 0, 1, 2 based, so 2 will indicate. So just let me erase this. So if I want to spell the suffix corresponding to position 2, I can always go back to the text and spell out the suffix. So in this case, 2 refers to this suffix CCP dollar. So given the suffix array and the original text T, I can recover all the suffixes. So to save the storage, I am going to only store this permutation of the suffix indexes ranging from 0 to 11. Let us take a look at another example. So this time with text T given as ATT, CAT, G dollar. Again, to build a suffix array, first we look at all the suffixes of this text T. So it has 8 suffixes shown on the left. Once we sort these suffixes lexicographically, we get our suffix array, which tells me the lexicographically ordered array of all the suffixes of text T. So again, because dollar is the lexicographically smallest suffix, dollar will occur first. Similarly, next will be ATG dollar, next will be ATT CATG dollar, and so on. In my suffix array, as I said just before, that I am only going to store these indices. If I need to know the suffix, I can always go back to my text and access the suffix starting from that position onwards. So this completes the definition of suffix array. Basically, it is a permutation of these suffix indices, and it gives you the lexicographically sorted order of all the suffixes. So given this definition of suffix array, we can ask, how does it help in pattern matching? So given a pattern P, and let us say you are given a suffix array of text T, how would we go about pattern matching? So how would we search for a pattern P? Similarly, we also want to discuss space complexity. So, how much space would a suffix array occupy and how much time will the suffix array take if we are about to build it. Okay, so let us start one by one. So, let us consider the pattern matching. So, let us say we are given a pattern P. How do we use suffix array to do fast pattern matching? Well, the key property of the suffix array is that you have access to all the suffixes of the text in sorted order. So, we are going to make use of that property and do fast pattern matching. So, for example, if my pattern is, let us say, T T. So, let us say my pattern is of size 2, which is T T. What I can do is I can run a binary search character by character. So, for example, I can run a binary search of character T using the suffix array. So, I can access the first column of the suffixes in the lexicographical order, and because these suffixes are sorted, I can do a binary search and find out which suffixes are starting from character T. So, through a binary search I can immediately get that the last 3 suffixes are starting from character T. Now, for the next character I am going to run a second iteration of binary search, and now within this particular range I am going to run the second iteration, and through a binary search again I will know that the pattern T occurs at the last row. So, very similar to the k-mer index, all we are doing is we are doing p iterations of binary searches. Therefore, the time it would take to do pattern matching using a suffix array is using this algorithm is p log t. So, this is fine that the time to search pattern P is order P log T, because we are doing P iterations of binary searches on an array of length T. This can be improved further, but that we will not discuss in the lectures. It is actually with more sophisticated algorithm, it is possible to improve this to P plus log T, but that is outside the syllabus. So, we are not going to discuss that. So, for us we will take the time complexity as P log T. Let us look at how much space the suffix array takes if you want to store it in memory. Well, that is easy to answer, because in the suffix array all I am doing is I am storing this T integers, and because each number ranges from 0 to T minus 1, I can store every element of this array in log T bits. Therefore, if I want to store the entire suffix array, I need T log T bits. So, that is good. So, we have quantified the amount of space that we need to store suffix array. Finally, how much time would it take to construct suffix array? Any guesses? Well, note that to build a suffix array we need to do sorting of all the suffixes of text T and there are T suffixes in text T. So, let us think of a naive algorithm, and let us think of any standard sorting algorithm like merge sort. Now, remember that when we are doing merge sort of an integer array, suppose we are sorting an integer array of n which has n integers, then we know that merge sort takes n log n time because it involves n log n comparisons. Now, suppose we were to apply merge sort here as well, then we know that merge sort will take T log T comparisons. However, observe that each comparison cannot be done in order one time, because now each comparison involves comparing two suffixes, and so when we are comparing two suffixes, we may need to spend order t time, because the length of this suffix is at most t. So in order to compare two suffixes, we may need to compare one character at a time. So for example, if I am comparing, let us say, suffix 1 and 2, then I will need to compare them one character at a time and then decide which of the suffix is lower or which of the suffix is smaller than the other. So therefore each comparison between two suffixes can take order t time, because we can compare them character by character. If we follow this naive algorithm of applying merge sort, where we just do merge sort of these strings, and keeping in mind that the comparison of strings can take order t time, this merge sort therefore would take order t log t times t time, because we are doing t log t comparisons and each comparison can take order t time. So therefore if we just apply a standard sorting algorithm to sort these t number of suffixes, we are going to end up with a time complexity t square log t using a standard merge sort on strings. So okay, so time to search pattern is okay, because we are sublinear in terms of the text. Space is also okay, but the construction time is actually not good. So if we are going to spend more than quadratic time, then scaling to large sequences like human genome or pine genome is not going to be possible. We need more efficient algorithms to construct suffix array. So just to summarize, so these are the properties of suffix array that we have studied so far, that searching pattern p can happen in order p log t time, space we need t log t bits, and if we just apply a standard sorting algorithm, we need order t square log t time. And we want to see, can we improve this construction time, because this quadratic time is too much. Well, it turns out that construction of suffix arrays has received a lot of attention in the computer science literature. If we look at the historically, there have been many papers that have been published and that have attempted to build faster algorithms to build suffix arrays. So for example, the initial attempts in 1990s came up with algorithm that have time complexity n log n, where n indicates the size of the text. So this is already better than the n square log n algorithm that we were discussing in the last slide. In early 2000s, linear time algorithms were developed for constructing suffix arrays. And in fact, I would say, I want to make a remark here that it is remarkable that suffix arrays can be constructed in linear time, because if you think about it, sorting of n numbers takes n log n, whereas now we are able to accomplish sorting of n strings, these are n suffixes, in actually linear time. So sorting of these suffixes can be done much faster than sorting of n real numbers. So this is the improvements that happened in early 2000s, and then there are more algorithms that came up that introduced various techniques in the motivation of developing faster algorithms that run faster in practice, but they may not have as good worst case time complexity as the previously known algorithms. In this table is taken from a review paper in which they also experimentally checked the runtime of these algorithms. So what this paper found was that the fastest performing algorithm was this paper from 2006, and relative to that implementation, how slow are the other implementations. So, for example, what they find is that the prefix doubling algorithm proposed in 1999 is 3 times slower than the fastest algorithm given by this paper. So, this was a thorough characterization of all the algorithms, and you can see that there is significant work that has happened to build faster algorithms for construction of suffix arrays. Now, we are not going to study them all because that will be too much for this course. We are going to take a look at one of them, and that will give you an intuition of how we can accomplish faster construction of suffix arrays compared to the naive algorithm that we just discussed a couple of minutes back. So, in this course we are going to study the prefix doubling algorithm that will take order t log t time in the worst case. So, this is not the best algorithm in terms of the worst case time complexity, but it is very close to that. So, t log t is very good compared to what we have here is t square log t, and the reason of choosing this prefix doubling algorithm is because it is relatively simpler, and it is also a very practical algorithm. The key property that we are going to use in this prefix doubling algorithm is following. Remember that when we were solving this sorting of suffixes using merge sort, this t square log t time complexity will hold for sorting of any arbitrary strings of length t. So, if you take a set of strings and each of these string is of length t, then this is the time complexity I would need to sort them. But in our case we do not have arbitrary strings, we have special property that all these strings are suffixes of the text. We have to utilize that property somehow to achieve a faster algorithm. So, in our case these 3 strings that we are given are not arbitrary, they are actually the suffix of the original text, and we have to use this property to develop a faster algorithm. So, let us see how that will be done. Before that, let me also give you actual numbers or to convey you that the prefix doubling algorithm that we are going to study is actually fast in practice. So, I am pulling these empirical results from a 2015 paper. What these authors did is they implemented prefix doubling algorithm and they optimized it for parallel machines. So, on parallel computers with 128 cores, so this is a cluster which has let us say 128 cores. On this cluster their implementation of suffix array construction for complete human genome only takes 22 seconds. In other words, they are able to sort 3 billion suffixes in the human genome in only 22 seconds using 128 cores, and that runtime further comes down to 5 seconds if they are able to use a larger system. So, on 1600 cores they are able to efficiently run the algorithm and construct the entire suffix array in only 5 seconds. Similarly, if I look at the Pine genome, the construction of the sorting of all 12 billion suffixes of the Pine genome takes only 15 seconds using 1600 cores. So, this is just to convey that the algorithm that we are going to study now to build this suffix array is actually very fast in practice as well, and therefore it is important for the real world implementations also. So, the plan is that we will look at the prefix doubling algorithm in the next lecture. For this lecture we are going to cover a prerequisite algorithm that is part of the prefix doubling algorithm. So, that is the radix sort. So, some of you may already be familiar with the radix sort algorithm, how it works, but we will just do a recall of this algorithm. So, let us look at how radix sort works. There are 2 versions of radix sort. One works by looking at the numbers from least significant digit onwards, that is left to right, and the other version works by looking at the most significant digit first and working from right to left. So, in this lecture we are going to look at the least significant digit version. we are going to abbreviate this as LSD. Okay. So, counting sort. So, let us look at the counting sort, because what we are going to do in the radix sort is we are going to apply this algorithm of counting sort multiple times. So, the way radix sort works is it looks at the numbers one column at a time, and in each iteration we are going to use counting sort algorithm. Now, here in the counting sort you can imagine that you are given an array of integers from starting from k1 until kn. So, you are given n integers, and all these elements are in the range 0 to sigma minus 1. So, the least all these values are greater than or equal to 0, and all these integer values are less than or equal to sigma minus 1. So, sigma minus 1 is an upper bound. As the output, like we want from any sorting algorithm, we want the output to be the values in non decreasing order. So, as the name suggests, counting sort is actually very intuitive. So, all it does is it is going to count the frequency of distinct elements, and based on those counts it is going to do the sorting. So, for example, just to give an intuition, so imagine that you are given these integers 1 0 1 1 2 1 3 2 1 2. So, let us say this is my input array. As a first step I am going to just count the frequency of distinct elements. So, in this case the distinct elements are 0 1 2 3. There are 0 occurs 1 times, 1 occurs 5 times, 2 occurs 3 times, and finally 3 occurs only 1 time. So, these are the counts. I am going to convert these counts into cumulative counts for convenience. So, cumulative counts. So, 1 6, then 9 and then 10. Now, this cumulative count will immediately allow me to sort this array. So, now all I can do is do a linear scan of this input array, and as I am doing the linear scan I know the position of each element in the sorted array. So, for example, when I start with element 1, I know that there is in my sorted array 1 should go at the second position, because from the counts I know that there is 1 occurrence of 0. So, therefore, I should leave the first element empty and I should put 1 in the second box. Similarly, I can know from 0 will automatically go to the first cell, the next one entry will go to the next one entry here. Similarly, we will keep filling these 1 entries. Now, the next entry 2, for that we can know that there are 6 entries which are 0 or 1. So, therefore, the number 2 must go at the 7th position of the array. So, I can directly put number 2 at the 7th position, and this is how the counting sort is going to work, that we will look at these cumulative counts and we will directly put all the elements directly at their correct position in the sorted array. So, here is a quick formal way of describing this algorithm. So, this is a pseudocode. Basically, all the pseudocode is doing is that first we are counting the frequency of the elements. So, all the distinct sigma elements we are going to count them, then we are computing their cumulative sums, right, and based on these cumulative sums we are going to do a linear scan of the input array, and we will distribute these elements to the final sorted output in array J. So, this algorithm actually requires a the runtime is linear in terms of the input array, and the runtime is also linear in terms of the value sigma, because here we are running a for loop of 0 to sigma minus 1 to calculate the cumulative sums. So therefore, the runtime of this algorithm is n plus sigma, where n is your size of the input array and sigma is the number of distinct elements, or sorry, sigma is the range of the elements of this array. So sigma is the upper bound of the elements in this array. So given this algorithm, we are going to use this algorithm iteratively in the radix sort algorithm. One important property of this algorithm is that the counting sort is stable. That is, if you have two elements of equal value, so if you see these are two elements that are equal, then their relative ordering in the sorted array is going to be same. So just I have done that through a color coding. So in this case, the red entry of 1 is going to occur before the green entry of 1 in the sorted array. That is, the relative order of equal elements is preserved in counting sort, and that you can check yourself by looking at the pseudocode as well. Okay. So remembering that the time complexity of counting sort is n plus sigma and counting sort is stable, let us look at how the radix sort will work. So as I said, the radix sort will work column at a column time. So now as an input, you can imagine that you are given a set of strings, each of length m, and let us say the alphabet is 0 to sigma minus 1. So this is the alphabet or the set of characters by which these strings are built, right. So now as output we want a lexicographically sorted strings. We are going to discuss the least significant digit version of the radix sort. By that means that we are going to start looking at these strings from the least significant digit onwards, which means that we are going to look at the least significant digit of these strings, and we are going to run a counting sort algorithm based on the values observed in the last column. So we are going to sort these strings based on the key observed in this column. So if we sort these strings based on the last column, what we get is, because the character m is smaller than character t, we are going to see that the strings that end with m will occur before the strings that end with t. So that is the first iteration. Now we are going to move to the next column, which is the second column, and we are going to repeat this algorithm. So again we are going to run the counting sort algorithm, and this time we are going to sort these strings based on their value in the second column. Again, because character A is smaller than character I, we are going to see that all the character strings which involve character A will appear first, and the strings which involve character I will appear in the end. Finally, in the last iteration we are going to sort all these strings based on the first column, and this time the strings that started with B and C will appear first, and the strings that are starting with H will appear later. Now one can ask, is how is this algorithm working? Why is this algorithm correct? So this is the last phase of the algorithm. This is where the algorithm stops. Well, the correctness of the algorithm follows from the fact that counting sort is stable. So for example, if you have strings, if you have values that are equal in this column, then their relative ordering will be decided by how we sorted their remaining part of the string, and depending on how we sorted these strings, the relative ordering will be preserved in the next iteration, because counting sort is stable. So both of these strings start with H, but because AM was ordered before IM, the counting sort will make sure that HAM will appear before HIM, because it is a stable sort. So mathematically one can prove the correctness by induction as well. So until ith iteration one can argue that the strings are sorted based on their last I characters, and at I plus 1th iteration these strings will be sorted based on their last I plus 1 characters. And again the stability of the counting sort will be crucial in making the argument, because the values that are equal at I plus 1th column, their relative ordering will be decided by how we did the sorting of the first I characters, sorry, the last I characters. So because of this stability of the counting sort, one can argue the correctness of this algorithm. Now what is the runtime of this algorithm? Well, you can see that we are just running counting sort multiple times. So because the length of this string are m, so we are running counting sort m times, and each counting sort will take s times s plus alphabet size, which is sigma, because this is the time complexity of the counting sort and this is how many times we are running this counting sort. So this is the worst case time complexity, and I will end by saying that this is the key ingredient of the prefix doubling algorithm that we are going to study in the next lecture. So in the prefix doubling algorithm, one key component will be radix sort of integers. So once we know once we have quantified the time complexity of the radix sort, we will be seeing that the prefix doubling algorithm, the time complexity of the prefix doubling algorithm will be much efficient, and compared to the merge sort based algorithm that we looked at for suffix array construction, prefix doubling algorithm will give us much faster way of building suffix arrays. Thank you.